Okay, so last week we have covered fluid dynamics. Okay, fluid dynamics, starting from the continuity equation. So from continuity equation, we know that the mass flow rate coming into a system is equal to the mass flow rate going out of the system. Okay, and this mass flow rate M, and the Q, the flow rate is also Q1 inlet equals to Q outlet, given that if it's a steady state condition. Okay, so now if there's a system in which there's a flow between one point to another point in a pipe or in any system, reservoir, or from tank to another tank, for example. So we can have a relationship or correlation between the 2 points. Okay, so we can use Bernoulli equation. Okay, this Bernoulli equation is an approximate relation between pressure, velocity, and elevation, and it is valid in regions of steady. So these are the assumptions that we need to make for Bernoulli equation to be valid. Okay, it must be in a steady state condition. Okay, incompressible flow, incompressible fluid. Okay, then where the net frictional forces are negligible. So it's frictionless. It is frictionless, where the fluid and the wall, we assume it has a zero friction. Then it's also called inviscid. Frictionless is also called inviscid. If the question say that it is inviscid, then it is also similar to frictionless. Okay, so friction forces are negligible. Then it is because we need to simplify the condition. We must simplify the condition in order for us to calculate dia punya pressure, velocity, and also the relation between the two points of in the system. Okay, then this Bernoulli equation is used mainly in fluid mechanics. Okay, and the Bernoulli approximation is typically useful in flow regions outside of boundary layers and wakes, where the fluid motion is governed by the combined effects of pressure and gravity forces. So you can see that Bernoulli equation is an approximate equation that is valid only in inviscid regions of flow. Inviscid means that it is frictionless. If there's friction, then we cannot say that the Bernoulli equation is valid. So you can see the region where the Bernoulli equation is valid is where the streamlines of the fluid. But if there's no streamline, then the Bernoulli equation is not valid. Okay. Net viscous forces are negligibly small compared to inertial, gravitational. Okay, so usually Bernoulli equation is along the streamlines of this fluid. Okay, so that are the assumptions or conditions at which Bernoulli equation is valid. Okay, if it is steady flow, so nothing change with time. Okay, so for example, in the figure here, okay, successive particle that pass through a given point will follow the same path. So meaning along a streamline, you can see a streamline, one line. Okay, there's one line here. Along a line here, this one line. The same particle will flow along this line. It will not go from this line to going to this line up here. Okay, it will not jump from one line to another line. So it will flow along the line. Okay, So these are the derivation of Bernoulli equation. We will not go through the derivation. Okay, you need to know how to apply the Bernoulli equation. It's just these are the long derivation lah. If you are interested to know how they derive the Bernoulli equation, the final one. Yeah, this is the final equation lah. This one. Okay, P over rho plus V velocity. This is the pressure. Velocity over 2 plus G, and the Z is the elevation of the particle. Okay. Okay. So final equation of Bernoulli along a streamline. Okay. On the same streamline, but between 2 points. Okay. Between 2 points, this is the final equation. Okay, after the long derivation lah. Okay, so what you need to know is this equation to be used if we have a system with that have 2 points that we can compare. We can compare the pressure, we can compare the velocity. Okay, so this is also how the Bernoulli equation is derived, because Bernoulli equation is it consists of these three element. Okay, the three element. You can see that one element is about the potential energy. Okay, potential energy, where it involves the height. The height, Z is the height of the point lah. If you have 2 points, to be compared, for the Bernoulli equation, we need to consider the height difference between the 2 points. If one point is higher than the other, then we have to take the difference of the 2 points. Okay, it must be in relation to what point. It's either you want to make the lower one is the datum. You must have a datum. Okay, your reference point, meaning that is your reference point, meaning that you have to choose you punya datum, your reference line. Okay, then we have the difference between the two point. For example, in this one, point 1 here, with point 2. So it has a difference in the height. This and this is the difference in the height. Okay, for example, in this one, it take this as the reference line, or you can have this one as your reference line. Then this will be you punya difference. Okay, then you punya Z2 equals to 0, Z1 equals to the level, the distance between the 2 points. Okay, that's the the potential energy, mgz. Okay, then we have kinetic energy, which involve the velocity. Okay, velocity. Then the other one is the pressure energy. Okay, involve the pressure. Okay, then it's also called in terms of head terms. Then we can say that when it's in head term, the unit is meter or feet. Okay, so the potential energy is Z. This is in meter or feet. Kinetic head is V velocity square over 2g, and the pressure head is pressure over rho g. So these are called the pressure, the head term, when its unit is in meter. Because Bernoulli equation can be written in 3 forms. Okay, so these are called the head term. Okay, where this is the hydrostatic pressure, dynamic pressure. Dynamic pressure because it involves velocity. This is a static pressure. It's not moving. Okay, so these are Bernoulli equation. This is a Bernoulli equation between 2 points. Okay, between 2 points, between point 1 and point 2. Okay, so this unit is meter. You can see the difference later. After this, you can, there's three terms, I think. This one is using potential head, pressure head, velocity head, and potential head. Okay, you can see the unit is meter. Okay, so these are the assumptions. As I mentioned just now, it must be incompressible fluid. Okay, the assumption must be incompressible fluid. it must be no energy losses due to friction. Fluid is under steady state. No mechanical devices in the system, meaning this is for this chapter before we go to energy. Energy next after this we will go into energy equation. Okay, this is Bernoulli, not energy, because we have after this is energy equation. So for Bernoulli, there's no pump, no turbine, no losses. Okay, we assume that, and no heat transfer. Okay, from point 1 to point 2. So that is Bernoulli equation. Okay, the simplest one. After this, when we go to energy equation, when we go to momentum equation, there will be more element to be included. Okay. So you in the questions, for example, if you see the questions say that all these assumptions is stated: incompressible, no friction, no turbine, no pump, then it will be Bernoulli only. Okay, but if let's say the question said that there's a pump in the system pumping the water from one point to another point, then you have to include energy equation. So that is a different equation. Okay. All right, so there are three forms of Bernoulli equation in which it's similar, but the difference is that the unit, okay, the unit is different. So you can say that the difference is in the unit. So you can see that this one is the unit feet or meter, okay. But for this one, when you times with the gravity, okay, there's no gravity here. Should be gravity over here if it's rho, right? If it's gamma is rho g. So this is no g, no g. So it times with the g, then the unit will be feet square over second square. Okay. This one times with the rho g with the gamma here. So it will be gamma is pound per feet cube times feet. Then it will be pound per feet square. So it's the unit of pressure. Okay. So it's just the difference in unit, because sometimes the question will give you some tricky question kan. Sometimes it will give you probably the unit with unit feet, or sometimes it will give you unit with unit pound per feet square, or it will give you sometimes with unit feet square over feet square per second square. So it can be any form. So you can choose which form that you prefer for that question. Okay, so it depends on the question. So if you have the Z is in feet, then you can use the third equation. So the equation number 3. Okay, but you just remember one. You can remember one equation, and you can just if it's different, then you can just times with the rho, or times with the g, or times with the gamma, in order to get the other equation. You don't have to memorize everything. Okay.